Hey everybody, it's John Broadwell, creator of the open source Serial Wombat project and technical resource for hire at my company, Broadwell Consulting Incorporated. Give me a call if you need help with something. Today we're going to be taking a look at the first video in a series on a robot I'm going to build with mechanism wheels, which are the wheels that can go sideways or rotate or whatever in addition to going forward and back. And I got this robot for 20 some bucks off of AliExpress. Uses 4 TT motors, these mechanism wheels. The nice thing is it comes with all of the hardware you need to build the thing up, including 2 of the sheet metal robot chassis, one of which has bent down sides to hold the motors, the other which is just flat for supporting your electronics and whatnot. So the first thing I wanted to do was to be able to build a model around this so that I can engineer how I'm going to put the thing together. And in order to do that, I wanted to create a model of the deck. And so let's go through how we're going to do that. In short, we're going to scan it. We're going to turn the scan into a black and white bitmap. We're going to take the bitmap and turn that into a vector in Inkscape. Then we're going to import the vector into Fusion. And from there, then we will take that vector and draw the shape of the thing and the cutouts and all those using minimalist, basically just lines, rectangles, arcs, splines, and the normal sketching tools. So let's take a look real quick at how you do that. Let's start with the scan. I'm going to scan the part, being careful when I set it onto the scanner not to scratch the glass with the metal, and then go into the Epson or whatever your software would be, and I'm going to scan it. In my case, I like to scan at 1000 dpi. That way later, if I want to take direct measurements off of the bitmap, it's easy because 1 pixel equals 1/1000th of an inch. And so basically, I'm just going to scan this in a very fundamental fashion to a JPEG that I can then import into Inkscape. Before we import the image into Inkscape, we will run it through Photoshop. We'll use the crop function to get only the part of the image that we want, and also its straighten aspect to try to get the image as orthogonal as possible. And we will also use the threshold and despeckle functions to try to clean up the image a little bit before we turn it into a vector. Next, we'll open Inkscape, and we will just drag the image from the file manager in Windows into Inkscape, and it'll show up. We'll embed it in the file. And then we will go up to Path, Trace Bitmap, and generally speaking, the default values work just fine. We'll go ahead and do that. And then finally, we will select Fill and Stroke. We will delete the bitmap, leaving only the vector, and then we will select fill and stroke and change it to a black stroke with no fill so that it's ready to go into Fusion. Now we're ready to import into Fusion. We're going to go to a new design, create a sketch on the top plane, and then go to insert SVG file and pull in the SVG. We'll say OK, and it will place it. That SVG file is almost certainly going to have the wrong scaling. And so we're going to do a measure inside of Fusion to see what one particular measurement that's practical for us to measure with a set of calipers on the real part is. And in this case, we will take the 2 kind of center sides of the metal plate, and we can see here that it's 38.48. Next, we will measure the real value on the metal plate using a calipers. And in this case, we see that it is 149.2 millimeters. Next, we're going to delete the existing sketch because it has the wrong scaling. Then we will insert the sketch again. This time in the scaling section of the dialog box, we will insert 149.2, which is the desired width, by the 38.48, which is the default width that we get when we import it, and that will properly scale the SVG file to the actual size that we want. The object we're trying to recreate is largely symmetric, so it will be convenient to have symmetry lines. We're going to create a new layer, and on that layer, we're going to, using vertical and perpendicular constraints, create some lines of symmetry that we will use so that we only effectively have to recreate 1/4 rather than the entire object. It's not entirely symmetrical. Some of the holes appear in some sides and not others, but for the most part, this will benefit us greatly. As we go along, you'll see us using the midpoint constraint, the collinear constraint, and locking and unlocking various items that we want to keep moved. One of the things to note in Fusion is that things that are green are locked. They cannot move. Things that are not green can move. And so you can see the entire bottom vector that we imported is locked. It will not move. And we're going to create our lines of symmetry locked so they can't move either. Next, we'll create another layer and do the outline of the part, which is what will be extruded, less the holes. We're going to start by, we're going to just draw the upper left-hand quadrant and then use the mirror function of the sketch capability to mirror it across the two axes that we created. We'll start by drawing all of the long straight lines, and then we will use either arcs, splines, or the chamfer option to create the curves. We'll use splines for things that don't have a constant curve. We'll use 3-point arcs for things that do. And for small curves, like the ones that essentially just round off corners, we'll use the chamfer tool. Those seem like the easiest ways to get this done to me. Ideally, when using the mirror tool, everything matches up perfectly across your line of symmetry. If you get a closed space, you get blue. Essentially, an enclosed area that can extrude turns blue on a sketch. In our case, we saw that that didn't happen right away. We had to zoom in slightly and add a couple of small lines connecting the sketch lines that cross the horizontal axis in order to get a closed shape. And once we did that, we were able to extrude it. Next, we're going to create a couple of layers for the holes that go through the board. We're going to create one layer for things that are symmetrical and one layer for things that are not. Right now, I'm just going to base this off of the sketch that I took. I didn't have any gauge pins handy. I ordered a set of these for this project. And so eventually I will put those in and gauge measure the actual size of the holes. And what I anticipate then is using the equal constraint on all of the holes that are the size, and also creating a parameter under modify parameters that will allow me to say how big I want a hole to be. Because, for instance, a 2mm hole may not print out to be 2mm on a 3D printer. So I may want to have a parameter to say, okay, I want a 2mm hole. What size do I need to draw it in Fusion in order to actually get a 2mm hole based on the print settings that I typically use? So we're going to go through and we're going to use a combination of rectangles and 3-point circles to do our best to reproduce the holes and slots and that are on this. We'll also use some arcs at the end of the long slots at the top, and note that we're using some perpendicular constraints and other things to create those slots as well. And again, we will use the mirror command to then mirror the holes that are symmetric across the various axes. Finally, we will add another sketch that covers holes that are not symmetric. So I took a calipers and measured the width of the plate. It is 1.6 millimeters. And so we will extrude the outline 1.6 millimeters to get a 3D solid object. Then we will use the two sketches that we created with the holes and do an extruded cut through the 3D object that we extruded from the outline in order to create our finalized board. Okay, that looks good. Let's save that as a mesh and put it into Ultimator Cura. I'll run it on my Elegoo printer, and we will do an actual 3D comparison of the model we built versus the real thing. And we know it's not going to be perfect. There's probably some holes that are not in the right space. Because of the way that the shadows fall through the scanner, it's never going to be perfect. But as you can see, in a very short amount of time, we create a pretty detailed copy of this thing. So let's take a look and see how accurately it fits. Wow, I really like that. Running over it with my fingers, holding it up either side to the light, I don't see much of the metal at all through the holes of the plastic, and I don't see much of the plastic at all through the holes of the metal. That seems like a really, really good start for us as we start to create our robot. And basically, there's a few things we could do with this model now. I can 3D print it. I can export it and laser cut it in other materials, or I could use it as the basis for an actual circuit board in the future, where instead of using wires, we primarily mount the components that we want on the board and run traces instead of wires. So that's very exciting. So anyway, like and subscribe to this channel to keep an eye on this mechanism wheeled robot project as it progresses. Till we talk again, have fun and keep making stuff.